Hello, my name is Chris, and on this show we are making games by year. What that means is we go year by year, starting at the beginning of the game industry. You, the viewers, pick a game that came out that year. We briefly talk about what was going on in that year, in and out of gaming. Then we discuss our chosen game specifically. Finally, we make our own version of that game from the ground up. It's a show for everyone, whether you're a developer or you're just interested in video games and history. You may have noticed this video is titled Episode 0. Episode 1 starts the show off in 1971, which was the birth of the commercial video game industry. This video acts as a sort of pilot episode and picks a game representing everything before that, from around the end of World War II through 1970. This was the Jurassic era of computing. There were no home computers yet, and mainframe dinosaurs ruled the Earth. But it was a time when academics and hackers were developing the first AI, the first 3D graphics, and even the first VR headsets. They also created games, of course. One of those early games is the very first version of Lunar Lander, created in 1969. This is the game we will be making today. Of all the early computer games that came out before 1970, you might wonder, why pick this one? A few reasons. First, it's recognizable. Throughout the decades, this is a game that has seen countless clones and derivatives. It's a game that might be more famous for being cloned than being played. The most famous and most cloned version of the game is the arcade game by Atari, which came out a full 10 years after this first version that we're looking at. The 1969 Lunar Lander game plays quite differently, being fully text-based. But this incidentally makes it a great Hello World program for our show. Additionally, the math required to understand the physics is simple enough that everyone should be able to follow along. But at its core, it's still a real game. It has an update loop that runs some simulated physics, changes the state of the world, gets input from the user, and then displays the current game state on the screen. So in a way, this game is a primitive version of every game. The things it lacks relative to later games, graphics, sound, and a more sophisticated game world, are all blanks we can fill in later, starting with this game as sort of a template or example. This is actually ideal for the format of the show, since as we go year by year, the games we make will get gradually more complex. The simplicity of the game means it's a game everyone can make. The original was around 50 lines of code written by a high school student. But at the time, it was seen as a great and fun game as well. It went on to become the most popular computer game of the era and inspired later games that improved on the formula. So, anyone can make Lunar Lander, but Lunar Lander is also every game, which means by simple implication that everyone can make every game. Hopefully over the course of the show you'll come to believe that this is true, given sufficient passion and hard work. So, let's make Lunar Lander. But before we dive into code, I'd like to give a little background on the game and its history. The year was 1969. It was the era of protests against the Vietnam War. It was a time of the civil rights movement and the counterculture. People were divided as civil unrest, protests, and even riots spilled into the streets. It was also the midst of the space race between the United States and the Soviet Union. Many looked to the space program not just as a piece of bitter Cold War rivalry, but as a triumph of mankind and a vision of a better future. This culminated in the historic Apollo 11 moon landing on July 20th of that year. One person who had the moon landing on their mind was Jim Storer, but back then he wasn't a professor of computer science. He was a 17-year-old attending Lexington High School in Massachusetts. In the fall, around the time frame of the Apollo 12 moon landing, Storer was enrolled in a computer class at school. It was during this class that he took his inspiration from the Apollo program and turned it into the game. To give you an idea about how unusual this was at the time, there was no personal computer industry until 1977, so when we're talking about early computer games like Lunar Lander, we're actually talking about mainframes. The school computer was the DEC PDP-8, a so-called mini-computer released in 1965 for the then shockingly low price of $18,500. It had 8 teletypes, a hard drive, and a total of 12K of memory. So Storer programmed his game on this machine. Then he mailed it in a DEC and forgot about it. But from there, the game's code was distributed and eventually spread to the entire early computer movement. Within 10 years, the game was described as far and away the most popular computer game. Alright, that's it for the history lesson. Now let's get ready to make the game. Before we actually make the game, we need to choose a programming language. We want something modern, but in the spirit of the original BASIC. So we want a language that checks all of these boxes, and Python fits the bill. Actually going step by step to teach non-programmers everything is beyond the scope of this video. But I know people who now develop professionally who only started programming when my friends and I gifted them a copy of this book. On this show, I'll do my best to keep a balance for the technical and non-technical audiences. So the first thing we need to understand is that at the heart of pretty much every game there is a core simulation loop that follows this basic pattern. Let's break down what all this means and then write a very basic example program. It's called a loop because we're going to do the same thing over and over again repeatedly. We update our game world. We first decide what objects we want in our game. This is called our game world. Then we decide the rules and laws of our universe. Then we apply the laws of our universe to all the objects in our game world every loop. For example, we update the locations of objects, or we take hit points away from an enemy, and so on. Doing this over and over again breathes life into our game world as the objects change over time. We get input from the user. This means we translate button presses, mouse movements, or typed input into simulated actions in the game world. For our simple game, we'll just be typing our input as text. We output the game state to the user. This means we take the current snapshot of our little universe and convey that to the user somehow. That's usually through graphics, sound, and the user interface. For our simple game, again, we'll just be printing text to the user. Let's start with a very basic example. We'll define a simple game world with two objects, a ball and the ground. The ball will start 10 meters in the air. The only law of physics in our game world is that every loop the ball will fall 1 meter. We'll output the state of the game world to the user by just printing the height of the ball. Here's what that looks like. We see here that the ball falls through the ground and keeps going. Detecting and handling the scenario when your simulated objects bump into one another is called collision detection. Let's add in some simple collision detection. We'll just stop the simulation when the ball goes below the height of the ground. Next, we want our simulated universe to take time into account. Notice that we don't actually know how long it takes for a ball to hit the ground, or even how fast it's going, because we don't know how much in-game time elapses between update loops. A single simulation loop updates the game world based on the events that happen in a discrete amount of time. This is called a time step. In real-time games, like first-person shooters, the time step is tied to the frame rate. In a turn-based game like ours, each turn will advance the simulation time by the same amount, regardless of how much time elapses in the real world. Our Lander game uses a time step of 10 seconds. A first-person shooter running at 60 frames per second has a time step of about 16 milliseconds. For this example program, we'll use a time step of 1 second. So now we know our ball is actually falling at a rate of 1 meter per second. In real life, a ball falling under gravity would keep speeding up as it approaches the ground. So let's add in some correct physics equations. For each game object, we'll track the position of the object and the velocity. Each update, we'll use Newton's second law to figure out how much each object is accelerating. We'll do this by adding up all the forces on the object and dividing by the mass. In our simple example, we know that the only force on the ball is gravity, so our acceleration is actually a constant. Then, once we know the acceleration, the current position, and the current velocity, we can calculate a new position and velocity using these equations. These equations are really easy to code up. So now our ball falls more accurately. Alright, we get the basic idea here. Now let's dive into how all the steps of our simulation loop pertain to our Lander game. Let's look at getting the user input. This section may actually be the most important to understand, since the set of actions the user can take at any given moment is what actually defines a particular video game and its gameplay. So what is the gameplay of our Lander game? In this specific game, the user types a string of characters that contains a number. This number represents the fuel burn rate for the next time step. The fuel burn rate will get converted into an acceleration from thrust. We'll cover how this works later. The more fuel burned, the faster the lander will accelerate away from the ground, but if you run out of fuel too soon, you'll probably crash. Python has built-in methods we can call to get the input we need. But because the user can type anything, we'll have to handle the difference between the user's input and what's valid input. For our purposes, valid input will either be typing quit to exit the game loop, or typing the fuel burn rate. So we handle unrecognized inputs by giving the user a chance to type something else. But even valid input needs to be processed. The lander has a minimum and maximum fuel burn rate, so we'll shut the engines off if it's below the minimum, and cap it to the maximum. For the sake of removing tedium, we'll also skip user input if the lander is out of fuel, so the game will just keep updating until we touch the ground. We have input, now let's work on output. For this game, the most important part is just printing all the relevant variables to the screen. We'll print a table. To do so, we'll use this fancy print syntax. It might look complicated, but all we're actually doing here is saying that we want to print our table using fixed width columns, 15 characters wide. We'll also add a message giving the player a little more direct feedback for when they run out of fuel. Now that we know how our game should work, let's revisit our sample game update method and change it to implement our actual gameplay. First, we need some numbers from the real world. We need the gravitational constant of the moon. We need the starting height above the surface of the moon. We need our minimum and maximum thrust. We need the mass of our fuel and the mass of our descent module. And finally, we need something called specific impulse. It might sound like a lot, but we're not actually changing all that much. Our generic physics equations update the game based on the object's acceleration. We already showed acceleration due to gravity, so the only new thing is taking into account the acceleration from thrust. We know from Newton's second law that if we have the force from the thrusters and the mass of the lander, we can calculate the acceleration. So all that's left is figure out how to convert the fuel burn entered by the player into a thruster force. This is where the specific impulse value comes into play. The specific impulse is a value that's related to the fuel burn rate in the thrust. With a little math, we can use this value to do two things. We convert the fuel burn rate the player enters on each turn into a thruster force that will apply acceleration to the lander. We can derive the constant for the max fuel burn rate. From there, we can easily derive the minimum fuel burn rate, then all that's left is to check our work before moving on to code. We'll add some class variables for the constants. We'll also add some variables to keep track of the relevant game state. We'll add a helper method for getting the acceleration from the player's input. We just use the equation from earlier. Then we use Newton's second law to convert the thruster force into an acceleration. This is a relationship between acceleration and mass, assuming that the force remains constant. As we play our game and burn more fuel, the lander gets lighter. This relationship means it'll be easier to blast away from the surface of the moon with the same amount of thrust. Let me show you what I mean. You have two landers. The only difference between the two landers is that the right one started out with half the fuel, and so starts with less mass. This makes it easier to accelerate away from the surface. Otherwise, the two landers are the same. They start at the same height, and they get the same force from the thrusters because they're burning the same amount of fuel each time step. So, putting it all together, our new time step does a few things. We subtract the fuel we burn during the time step from our total fuel level. We increment our mission time. We calculate our total acceleration. We'll add the acceleration due to gravity and the acceleration from the thrusters. And finally, we update the position and velocity, just like we discussed before. The next thing we want to do is take our simple simulation loop and turn it into an actual game program. So we'll take our simple simulation loop and augment it with some extra steps, so that it looks like this. First, we'll wrap our entire game loop with an outer loop that asks the player if they want to play again or quit when their game is over. Next, we'll look at the initialization step. We'll set the initial values of some gameplay variables. We also print the story and instructions. We can put the story and strings directly in the code, Or we can print the contents of a plain old text file in order to make the story easier to edit apart from the game code and to keep things decluttered. We also need to detect win and loss conditions. In this game, we just need to detect when we hit the ground. This game has 4 different endings. You'll get a different ending depending on how close you were to the ideal landing speed when you touch down. Finally, we'll add a bit of additional polish. When you crash, we'll make up some crater depth based on how fast you were going. And, as a personal touch, we'll let you type your historic first words on the moon when you touch down. And we're done. It's an actual playable game now. We made a game, so let's play through it once. Our game doesn't have any graphics, so to make things more interesting, I hired a professional cartoonist to illustrate what the game would look like if it actually did have graphics. Our pilot is clearly asleep, so we'll just type 0 for the thruster input. And again. Our pilot wakes up at the last second and fires the thrusters full blast. But unfortunately it's too little too late. Now that we're finished with our game, I'd like to take the opportunity to do a little compare and contrast. This is Steve Russell's Space War from MIT in 1961. DEC actually used it as a diagnostic when shipping PDP-1, since the game used every bit of the system, making it sort of the Crysis of the 60s. But if you break down the features, it's not insurmountably more complex than the game we just made. Space War just adds graphics, moves the physics into 2D, and just has more of everything, more objects and more forces on those objects. As the show goes along, it should be pretty painless to build on what we learned here to make more complicated and interesting games. Alright, that about wraps it up for Lunar Lander and our episode 0. In the next proper episode, episode 1, we'll be visiting 1971, the year of the first commercial video game. That game is Computer Space, which was an attempt to bring Space War to the arcade. It was created by Syzygy, which would later become Atari. Another notable game that year is Galaxy Game, another attempt to turn Space War into a commercial arcade game. This one was much more faithful, but didn't see widespread release due to its impractical cost. Then there's this unofficial Star Trek game, which I remember playing a version of with my dad as a kid. And finally, we had the earliest, non-commercial version of the Oregon Trail. It was all text, but other than the hunting minigame, the difference is more or less just cosmetic. So, of all of these games, just put which one you'd like to see in the comments, and the one with the most votes will be the next episode. If people want me to stream these games to help them decide, maybe that can be arranged too. For now, thank you for watching. I hope you had fun, and I hope you join us next time on Making Games by Deer.
Sugar, oh honey, honey, you are my candy girl, and you got me wanting you, honey, oh sugar, sugar, you are my candy girl, and you got me wanting you. I just can't believe the loveliness of loving you. I just can't believe it's true. I passed a horse of carriage, but you, sweet pasta, sita, bicycle, built for